Hi, my name is Qi. I'm a second-year PhD at Carnegie Mellon. Today I'll be presenting BOAT, a privacy-preserving inference system for transformers. This is a joint work with my awesome collaborators, Jinhao, Helen, Wenting, and Thomas. So let's get started. Transformer architectures have become the foundation of many modern machine learning models. For instance, models like GPT, BERT, and VIT are all based on transformers architecture. And many high-quality models have emerged that outperform human beings in many tasks. And companies like OpenAI and Google are also providing model inference services for users. Thanks to the powerful performance of transformers, machine learning as a service is becoming very popular, and there are many applications deployed in the real world with transformers as the backbones, including the chatbot, translator, and many virtual assistants. But the privacy is still a major concern in this field. For example, in March of 2023, ChatGPT was temporarily banned in Italy due to data privacy concerns. And one of the violations was that the user's inputs and chat history are revealed to OpenAI in Clear. Such inputs can leak a lot of privacy information of the user, like the user's identity, their hobbies, etc. Uh, there are also many companies banned the use of generative models for their employees to prevent commercial data leakage. So it is urgent to deploy a practical secure inference system for transformers to rigorously protect the user's privacy. And our question here is that can we perform privacy-preserving inference without revealing parties' private inputs to each other? So to answer this question and solve this problem, let's firstly make the settings clear. In the following, we consider semi-honest parties. They will honestly follow the protocol, but they are curious about the other party's data. And the client has a private input, and the server has a confidential model. So directly sending the data to the server will leak the private information to the curious server. And similarly, sending the model to the client will leak the confidential model to the client. To protect the private data from both parties, cryptographic techniques provide a feasible solution, such that all the exchanged messages are encrypted and only the final output is revealed to the client. And most of the secure ML inference systems, including our bot, are based on cryptographic primitives like secure multi-party computation and homomorphic encryption. And here we primarily focus on the secret sharing-based two-party computation. And 2PC usually has higher communication overhead, but it has the capability of evaluating complex nonlinear functions. And homomorphic encryption has relatively lower communication costs and higher compute overhead, and it's more efficient to evaluate linear operations. To reduce the communication costs and improve the efficiency, we built a hybrid protocol by using HE to evaluate the linear layers and using the complex nonlinear functions are evaluated in 2PC. And conversions between 2PC and HE is feasible as we can switch the modulus by evaluating comparisons in 2PC. One of the state-of-the-art work on secure transformer inference also built a hybrid protocol to compute linear layers in HE and nonlinear layers in 2PC. However, due to their sparse ciphertext packing and complex nonlinear functions, they need huge communication cost. For instance, for a single secure inference on BERT-based model, which is a widely used transformer model for text classification and regression tasks, IRON requires about 881 gigabytes communication resulting in about 3.5 hours runtime in the one network setting. In contrast, by co-designing machine learning and cryptographic primitive optimizations, our system both can significantly reduce the communication overhead in both linear and nonlinear layers and achieve about 10x improvement in runtime performance. So to address these challenges, we propose novel ciphertext matrix multiplication algorithms and incorporate baby step gen step to reduce the number of ciphertext rotations in linear layers. And we design crypto-friendly approximations as well as polynomial preprocessing to reduce the number of multiplications between shares to improve the efficiency for nonlinear layers. And additionally, to further improve the efficiency, we also incorporated the novel optimizations from machine learning's perspective. Now let's start from the overview of both. Let's start from this sentence. It will be firstly tokenized and embedded into a matrix by the client. Then the client will encrypt the matrix, encrypt the input matrix in homomorphic encryption and send the ciphertext to the server. And server will feed the encrypted tokenized input matrix into the transformer model, where the linear layers are evaluated in homomorphic encryption on the server. As the nonlinear layers like softmax are evaluated in 2PC. There are several feed-forward layers with normalizations and the complex nonlinear function GLU in the transformer, and this forms the one transformer block, and the output of this block is fed into the next block, and we have 12 blocks of board base in total. Finally, the last transformer block is connected with a pooling and classifier layer, which will output the encrypted final prediction. And the encrypted prediction is sent back to the client, and the client will decrypt it in HE to get the result, which is a positive sentiment prediction. Now let's address the first challenge in linear layers. I will primarily talk about our novel packings for ciphertext and plaintext matrix multiplications, and you can find more interesting techniques about the other techniques in our paper. Let's briefly introduce some important facts about the levels of homomorphic encryption, and here we use BFE in our protocol. So BFE encodes a vector of integers into a polynomial of degree n and modulus p, and the polynomial is encrypted into a ciphertext with degree n and modulus q. For example, the vectors a and b are encoded into the plaintext polynomials and encrypted into ciphertext polynomials, with their values represented in the NTT space, and the SIMD operations are supported to improve the efficiency. Typically, there are several operations supported by BFE. The additions will give the element-wise addition result of two vectors, and multiplications can be performed between two ciphertexts or ciphertext and plaintext, and the element-wise multiplication result is returned. Additionally, rotations can be performed on the ciphertext, and the elements' positions in the vector will be rotated cyclically by an arbitrary number of steps. Usually, the additions in homomorphic encryption are relatively cheaper, and the multiplications and the rotations are much more expensive to compute. And we can only do a limited number of multiplications in leveled HE as they will consume much more noise. Now let's firstly introduce the linear solutions in iron. Let's consider this x times y. To eliminate the rotations in homomorphic encryption, iron encodes x and y into the coefficient space of the polynomials instead of the entity space, and they carefully decide the positions of the values. So the high-level idea is that if we carefully organize the values in the coefficients of two polynomials, we can get the inner product result by multiplying these two polynomials together. Like we are showing here, to compute the inner product between the first row of x and the first column of y, iron simply multiplies the two polynomials of x1 and y together, and the inner product result will be the coefficient of x to the 1 in the resulting polynomial z1, which is the first element in the result z. Iron computes the inner products of other rows and columns in a similar way, so by extracting the certain coefficients in the resulting polynomials, iron can get the correct multiplication result z. As you can see here, there are a lot of useless polynomial coefficients in the ciphertext, and we mark them in red here. They will cause significant communication overhead by sending the sparse ciphertext back and forth. So if we take the concrete dimensions of a bird, we can see that iron greatly improves upon prior work Gazelle, which is specifically designed for vector matrix multiplications. But iron still requires sending a large number of ciphertexts, which is 56 here for for a linear layer in BERT-based model. So iron eliminates the rotations in HE to reduce the compute overhead. However, they unavoidably waste a lot of ciphertext slots, resulting in high communication overhead. To further reduce the communication cost without introducing too much compute overhead, we propose a different packing method to achieve compact packing in the ciphertext. Specifically, we pack the input ciphertext matrix X in column-wise and pack the plaintext matrix Y diagonally, but repeat each element for m times, where m is the row number of X. And the values are encoded in the entity space instead of the coefficient space. Then we rotate the ciphertext to swap the positions of the different columns, and here we only need to rotate once. And then we multiply the corresponding ciphertext with the plaintext, and add the result together, we will get the multiplication result. And for this concrete example, we only need one rotation and two multiplications, and both the input and the output ciphertext are compact. Again, if we take the concrete dimensions of BERT, we can see that the number of ciphertext assigned between the server and the client is minimized, which is 13 here, and we are not increasing the number of multiplications. By further incorporating the baby step gen step, we can significantly reduce the number of rotations. So the high-level idea for BSGS is that instead of rotating the input ciphertext only, we can delay some rotations to the partial results to achieve and optimize the number of total rotations. So please find more details in our paper. As the cost of single rotations and multiplications are comparable, thus, we can significantly reduce the communication by increasing the compute overhead by about 5%. So BOLT has compact ciphertext packing, and the number of ciphertext rotations is optimized by BSGS. Thus, we can significantly reduce the communication cost without increasing too much compute overhead. So this is our solution for linear layer, and now let's introduce a polynomial preprocessing for the nonlinear evaluation, and you can find more details about the crypto-friendly approximations in our paper. So for GLU, we use its linearity and symmetry to approximate it using a 4-degree polynomial, as we show here. And the 4-degree polynomial is evaluated in 2PC. And the insight here is that the coefficients of the polynomial are publicly known so that we can apply the polynomial preprocessing to reduce the number of multiplications between shares. A naive way to evaluate this 4-degree polynomial is to calculate 3 multiplications between shares. However, with Moskins polynomial preprocessing, we can construct two sub-polynomials in the following manner, where the G0 to G4 are constant public values independent of the input. Thus, we only need 2 multiplications between shares instead of 3 now. And generally, if we want to evaluate a public polynomial of degree n by using the Moskins polynomial preprocessing, we approximately need n over 2 multiplications between shares. So the takeaway here is that the Moskins polynomial preprocessing can significantly reduce the number of multiplications between shares when the function is public. And this technique can be applied to generic polynomial evaluations in cryptographic primitives to improve the performance. We also incorporate machine learning optimizations to further improve the inference efficiency. And here we will introduce oblivious word elimination, which significantly boosts the inference efficiency by eliminating the unimportant tokens in the input. Let's consider this input sentence again, and the model is predicting its sentiment. So intuitively, not all the tokens in this sentence contribute equally to the prediction. Like the token charming and affecting will make more contributions to the prediction, and the other tokens are not as important. So all we need is to compute important scores for these tokens and only keep a portion of the tokens that are more important. Unfortunately, the self-attention mechanism in transformer offers a natural way to calculate the importance score for the tokens. Specifically, in the first transformer block, the softmax output measures the pairwise correlations between the tokens. So, by summing the m by m attention matrix along the rows, we can get an importance score vector. Then we sort the rows of the attention matrix using this importance score vector as a key in 2PC using oblivious sorting like Bytonic sort. Then we eliminate half of the rotations by uh, eliminate half of the rows by dropping the last half of the rows. For the subsequent transformer computations, we can successfully reduce the cost by more than half. And soon in our evaluation, we will show that this word elimination has a negligible influence on the model's accuracy. So now let's evaluate both. We first introduce the evaluation setup. We evaluate both on a widely used transformer model, board base with 110 million parameters. Our evaluation is conducted on 4 datasets from a commonly used glue benchmark for board evaluation, and these 4 datasets include text classification and regression tasks. Our experiments are run on 2 AWS instances, and we use a thread number of 32. We consider different line and wine network settings with different bandwidths and round-trip latencies. We primarily evaluate 3 metrics, including model accuracy, communication overhead, and end-to-end runtime. We compare to a state-of-the-art secure inference system for transformers iron. Firstly, we show that the accuracy for both with and without word elimination matches the plain text model's accuracy and is comparable to iron. And we further measure the communication cost of different components in both. And here we are showing the cost of a linear layer and the nonlinear function GLU. The different bars represent different systems, including iron and both, with and without word elimination. The y-axis is showing the communication cost in megabytes. As expected, our linear and nonlinear layers save a lot of communication, and the word elimination saves about 2x of the communication cost. So for end-to-end communication, both can reduce the communication cost by nearly 11x compared to iron. And finally, we benchmark the end-to-end runtime of both and iron in different network settings. The y-axis is showing the runtime in seconds, and these 2 figures have different network settings, including the local area network and the wide area network. Both is about 5.2x faster in the line network setting and 9.5x faster in wine. So to conclude, we propose both a privacy-preserving, accurate, and efficient inference protocol for transformers, and we incorporate novel optimizations from both cryptographic primitives and machine learning's perspective. We significantly enhance both inference performance, advancing towards practical secure inference for transformers. So that's all of my presentation, and thanks.